Exponential functions are functions which include a constant raised to a variable power, as compared to polynomial functions, which are variables raised to constant powers. So those roles are reversed. Exponential functions are an entire class of functions which have a great deal of number of useful applications in the world. Anything that tends to grow or decay tends to be represented through some kind of exponential function. So this chapter, we not only introduce those, we actually spend most of our time focusing on the inverse of exponential functions, which are called logarithms. And logarithms have pretty rich history to them, but we're going to use them primarily to solve equations that involve exponential functions. So let me begin with a very simple exponential function, y equals 2 to the x. And so as you see, we have a base number raised to a variable power x. And now the base can be any constant number as long as it's positive and not equal to 1. So, for example, in my book, I define a simple exponential function to have this form, where b is a constant that's positive but not equal to 1. You can see what happens if b is equal to 1. Then you would have this function, and 1 to the x would just simply be 1. It wouldn't be an exponential function, it would be a constant function. So we keep the base positive because negatives would be a real problem. For example, what if you had y equals to negative 2 to the third power? Okay, that's not a problem. That would be negative 8. Negative 2 times negative 2 times negative 2. What if this was to the square root of 3 power? Now we have a real problem, because we don't know if this is supposed to be negative or positive. Is it a complex number? What in the world is that? And so it's that kind of issue is really beyond the scope of this course. So we're going to keep it simple and stick with only the positive bases, where this number inside is positive. It's not that these aren't in a way interesting, but they're really not. I'm not aware of any applications of those types of exponential functions. All right, so y equals 2 to the x is really one of the easiest ones to begin with. And if you had no idea how it behaved, then you would want to see some kind of picture of it. So I'm going to form a little xy grid here, or xy chart, and we'll plug some x numbers in. If x is 1, then y is 2. If x is 2, 2 to the second is 4. 3, 2 to the third is 8. 4 would be 16. And you see what's happening here. As I increase my number, what's happening for the y's? They're doubling. I mean, the next one's going to be 32. 2 to the fifth power would be multiplying 5 2's together. You get 32. Alright, so these numbers are getting big rather fast, which is interesting. Let's go backwards and look at 0. And 2 to the 0 is 1. And 2 to the minus 1 is 1/2. And 2 to the minus 2 is 1/4. 2 to the minus 3 is 1/8. Alright, so this is just, from the rules of exponents. If you're a little rusty about those things, when you have a number raised to a negative power, for example, 2 to the minus 2 would be 1 over 2 to the positive 2. So when you change an exponent sign, you invert the fraction, or invert the base. All right, and a 0 power, anything raised to 0 is going to be 1. Well, almost anything. 0 raised to the 0 power is a real problem. But let's not get into that now. All right, well, let's see what this looks like. And it looks like all the y values are positive. And in fact, they are. A base number, a positive number raised to any power you can think of is going to be positive. So that means all the y values are going to remain positive. All right, so I think I'll go out, about 3 units either way. And we'll go up to 8. 1, 2, 6, 7, 8. Here we go. So we'll plot these points. 1 comma 2 be over 1 up 2. Then there's 2 comma 4 and 3 comma 8. Sorry to stand in front of this, but I want to get it kind of accurate here. 4/16 is above my graph. 0, 1 would be right on the y-axis. Now I've got 1/2, 1/4, 1/8. All right. Now I hear my dog in the other room eating and crunching and making a lot of noise, so I'm going to close this door here for a moment. Okay, sorry about the interruption. I don't know if you could hear that, but I could. She's a noisy eater. All right, well, look what these dots are doing. They're rising quicker and quicker on the right side, but on the left side it looks like they're flattening out. And so to connect this with a smooth curve, looks like it goes up that way. And I'm going to put a few scale numbers on our graph. Any graph should always have some scale numbers. Now I'm not a big fan of numbering everything on a graph, but as long as the reader can tell what scale you're using, that's all necessary. All right, so here's our graph of y equals 2 to the x, and it's an example of exponential growth. So I'm going to call this exponential growth. Now, it turns out a lot of things grow exponentially, especially when there's nothing to check its growth. For example, populations, whether it's people, animals, plants, things like that. Populations tend to grow exponentially when there's nothing to stop the growth of that population. Well, with humans, there's really nothing to stop the growth of a population unless there's a very devastating war or a famine that would slow us down. But so human populations tend to grow this way. So do insects if they get in your house and start multiplying. If there's no predators and if there's plenty of food, then they'll take off exponentially. Even companies, if a new industry enters a market and is pretty much unchallenged, alone in that market, its growth will tend to be exponential as well. So it's quite interesting. I'd like to talk more about that when we get to a later section about this and where this growth comes from.